Hello. In this lecture, we're going to take a slightly different tack. We're going to look at a particular kind of evidence, to wit, digital photographs, and we're going to see what some of the interesting issues are concerning how they differ from traditional digital evidence. In this presentation, we're going to be talking about some of the issues regarding doing forensics with digital photographs. It's not surprising that this has become a bigger and bigger issue. We're going to start with the notion of some basic forensics concepts and look at how photo forensics is a little bit different, talk a little bit about photo file formats, and talk about active recovery versus deleted recovery. The first issue is, why is this fundamentally different from regular forensics? Well, it's not fundamentally different. It's still file structures that we're trying to recover, but these particular file structures tend to be large. They tend to be largely binary, and they contain lots of information both at the metadata and the file level, in addition to the content. So I guess we need to start by saying, what is this photo forensics? And it's basically forensic investigations that involve looking at digital photographs. And one of the things that's pretty obvious about that is that they're pretty important and they're pretty useful, because the old story about a picture is worth 1,000 words is probably true even more so now than it used to be. The photos themselves are becoming far more common. As the slide says, there's over 2.5 billion photos per month put up on Facebook, and the Flickr has over 4 billion photos. Now hard drives can have thousands of photographs. As some of you may know, I'm a photographer, and my ready storage on my desktop is typically somewhere in the 10 to 20,000 photographs. And that those photographs are actually very large. In many cases, the files themselves are up to 25 megs per file. So 10,000 of those is a large chunk of data and a great deal of information. Not only do we find the photographs all over the internet and therefore find them in our subjects' computers, but we have more and more tools to create them. And we'll talk a little bit more about that later on. But the one nice thing about photographs is they can tell us a lot about the who, what, when, where, how, and why. Because we tend to collect photographs that mean things to us, that represent places we've been and activities that we've done. And these are all very useful when you're trying to identify a subject or identify what a subject has done. It can provide us with all kinds of information about places he's actually been or whether they have alibis, and certainly they're linked to a lot of the correspondence that people use on a daily basis. One of the most explosive parts of this is that now almost everything we touch seems to have a camera in it. Not only do we have digital SLRs and compact pocket cameras, there are better and better cameras in all of our cell phones. We have all kinds of other video devices now that are relatively small, and so we're starting to see digital cameras very ubiquitously. And we not only have the scanners, not only the cameras, but the scanners as well. And the distribution mechanisms include email, the web, and peer-to-peer. The slides make an interesting point. It's very often that the real crux of the photo forensics is trying to determine the difference between content creators, content distributors, and content consumers. Content creators being ones that actually produce this particular content. Content distributors are those that are sending this information around, and content consumers are people that are actually reading or collecting this information. Obviously, in the case of kiddie porn, this is really important, but it's also important in lots of other cases as well. Photo forensics in some ways is no different than any other forensics in that the first step is recovery. And there's essentially two ways of doing that. One is the more normal active data recovery, and then file carving becomes a really important issue. Once we've actually recovered all of our photos, then organizing them is really important, because we actually have to put our two highs on all these things. And so if we're going to get any value out of them, we have to organize them in some fashion. And this is one of the things that some of the specialized photo software tend to do pretty well. And then the content analysis. And this is a little bit trickier, because it's really talking about what is the photo about. Why was this photo taken, and what is it showing? This has become easier in some areas and harder in others. Classification is really about how do we make use of this in a forensic setting. Attribution is, of course, who or what took that photograph, and authentication is it real? One of the issues is that there are dozens and dozens of digital photo formats. We're going to cover a few of them here in this lecture that are the most popular. And certainly the single most popular is the JPEG. And there are a number of varieties of the JPEG, but pretty much it's probably the most common digital file format, or at least for photos. But there are also PNGs and GIFs and RAWs and TIFFs and all those sorts of things, which we're going to talk about in a while. And bitmaps, BMPs, used to be popular, but they've really kind of fallen by the wayside because they're not scalable. You can tell typically what a digital image is in terms of its file format by looking at the extension. And a JPEG typically has a JPG or JPEG extension, whereas PNGs have PNG, GIFs, etc. The DNG format is an attempt to have a standard raw format for all digital cameras. It's not getting a great deal of traction right now. It still is in its infancy, and it's to be seen whether or not it becomes a cross-platform standard. Nikon and Canon each have their own RAW formats, as does Sony. And you would think that a RAW format would be a RAW format would be a RAW format. Well, it's not. And so they have their differences, and they're not interchangeable. TIFFs are usually much larger images, and they are not typically compressed. As the slides say, Windows tends to use that extension to determine what program should be used in order to open it. And just changing the file extension is enough to either hide or obfuscate information from Windows itself. And for that reason, we need to take a little bit deeper view of some of these things in order to figure out where we're going with them. JPEG actually stands for the Joint Photographic Experts Group. It's a standard that's been around for quite a while. It's in its, I think, third iteration now. And it has the ability to handle complex images. It uses what's called lossy compression, meaning that some of the detail is removed as the image is compressed. And with JPEGs, typically you have the ability to decide just how much compression you want to use to try to make the file smaller. And obviously, the smaller you make the file, the less detail that you're able to save. JPEGs are good for images. They're not terribly good for letters and drawings and graphics. And most devices, most cameras, the default format is JPEG. And it's the most commonly used to share photographs among users. And just about every piece of software in every system supports JPEG. The other thing is they talk about progressive JPEGs. The JPEGs are stored in such a way that they can be downloaded to the web fairly quickly. GIFs, on the other hand, stands for Graphics Interchange Format, and it was designed as a way to move graphics over relatively small, relatively slow networks, and it could also be used for small animations. And it supports 256K of color, which is not very much by today's standards. And it's usually used occasionally for like slide graphics and that sort of thing, and for icons and things like that. But one of the things that is useful is that when you find them in the cache, they're very often obtained from visiting a website. So that's usually a good way to do that. PNG is a patent-free storage system. It's similar to GIF, but it has the ability to utilize a full palette of colors, and it's really used typically for storing originals because it does not use compression, so that it retains all of the original detail. Bitmaps were the original Windows format. They're very often used for graphics and icons and stuff on your computer and your desktop. There's many variations, but the most common is 24-bit, and it's not very often used for photographs because, again, it's not very scalable. The program that writes these things is Windows Paint, and it really isn't the greatest format out there, but it was a small format, which at the time was good because of the limited bandwidth, and of course it also did well because it was a Microsoft format. TIFFs, on the other hand, tagged image file formats, were originally designed for scanning stuff and for faxes. It had a pretty good level of resolution, but now the structure of it is such that it acts as a container for one or more other objects inside of that container, and it can actually include raw JPEG and PNG files within the TIFF image. TIFF is also very often a format utilized for intermediate level editing of photographs. RAW format is in some ways the analog for cameras, what a forensic image is for those of us in forensics. It basically is capturing every single pixel, and in fact every value of each pixel in terms of the red, green, and blue, and because of that it has a lot of data, and that data is good data and can be used to generate images that are processed to get the maximum amount of resolution, the maximum amount of color, dynamic range, and that sort of thing out of them. So they're very useful, particularly for professional and semi-professional photographers. The problem is that you need specialized software to process them, because, as we said earlier, the Canon version is different from the Nikon version, which is different from the Sony version. You'll typically see RAW either on digital SLRs or high-end compact cameras. You don't typically see them in the cheaper pocket cameras. The RAW format is very large. It typically is at least one, if not 1.5 times the size of the number of pixels in the original image. So it's big. DNG is Adobe's attempt at trying to standardize a RAW format. It's actually a type of TIFF, and it's open standard, so anybody can use it. Lots of software provides a way to convert to DNGs, but not a lot of people take the extra step to have their images processed in DNGs, just because they've are already going to spend a lot of time moving these images around and reprocessing them. JPEG 2000 is an updated JPEG standard. It was used for a little while. It's not very common anymore. It uses both lossy and lossless compression. We say lossy, it means that it removes some of the detail, whereas we say lossless, it retains all of the original data in there. It compresses better than JPEG, but it's not particularly efficient at doing it, so it takes a lot more computer horsepower to do it. Adobe, in their Photoshop program and some of their spin-offs like Adobe Elements, utilize the PSD format. The PSD format is in some ways a TIFF on steroids, because it not only contains the original and all the data in the original image, but it actually includes things like layers and also the modifications that were done to a photograph. So when you have a PSD, it's captured all the things that you've done to it so that it's a reversible process. From a forensic perspective, PSDs are good because it can help us determine what the original image really looked like. But at the same time, if we're going to do any photo enhancement and that sort of thing, we want to save the PSD file because it will provide us with a list of all the stuff that we've done to it along the way. The WMF Windows Metafile format is used primarily as clip art for Microsoft Office products, and WebP was Google's lossy format. It's supported in Chrome, but that's about the only place you'll see it. And this particular image here shows you a PNG uncompressed. You can see it's very smooth, very detailed, whereas a GIF, the colors are not very even, the resolution is not very high. The JPEG low compression, you can see that it's a little grainy, and that actually should be, I think, high compression, not low compression, because the medium compression to the left of it you can see is much clearer. So I think that slide is incorrect. Hopefully by now we all understand that a pixel is a single dot of color and that photos are made up of lots of pixels. And the resolution is the number of pixels in width and the number of pixels in height. And then there's also the value of what's called color depth. And that's how many bits make up that color that is observed by the sensor. A megapixel is nothing more than the pixels divided by a million, in some cases 1024. There are different formats as well. You can see that the picture on the right shows you the native resolution, the native size of a 1.3 megapixel, 2.1, and so forth. But we also have sensors that have different formats as well. And so that impacts the size of our photos, both in terms of the number of pixels and resolution, but also the size of the image itself. Aspect ratio is just the height versus the width of the actual image. In the old days, it was pretty much fixed. You had what you had, and the film controlled that. Now with digital cameras, we have the ability to vary that to include making things high definition, 1024 by 768, or 16 by 9, which is the widescreen format. So it provides us with a lot more control over our images. Metadata is more important in photographs perhaps than in any other form of data, because it not only describes the attributes of it, but it very often contains a lot of information about the actual device that created the image. You will find this metadata in JPEGs and RAW and TIFF images, and you will very often find different sections of that metadata. The EXIF information, which is about the image and how it was taken, the IPTC, which is the ownership information, and XMP, which you also occasionally see as what's called a sidecar. It's a file that gets stored along next to the original image, and it includes more data about the image itself. Metadata is typically divided into tags and values, just like a registry is. The tag in this case is EXIF, is the area of the data, and then the image, and then the model section. And the value for that image, exif.image.model, is Canon PowerShot SD700IS. EXIF data is the exchangeable image file format. It's the most common metadata that we have in all of our pictures. I don't know of a manufacturer that doesn't implement it. In fact, it's usually very, very difficult to get rid of. The nice thing about it is that even though there are some differences in it, typically the maker is kind enough to tell us about it so that we know what it is that we're looking at when we look at EXIF data. EXIF data typically contains the date and time and the computer's camera settings, typically an embedded thumbnail, and that's used for previewing the photograph, and descriptions and copyright information, and in many cases now it has GPS information. Now we're going to go next into the recovery and carving, and in some ways this is very similar to what we've been doing all along, but in the end photos are stored like any other file. As a result, they live and die by the rules of that particular file system. So NTFS, FAT12, FAT16, HFS, HFS Plus, all define how this data is going to come out. We typically store our photos in usual PC file systems, even if we're doing them in removable cards or inside the camera itself. Even in a lot of cell phones, they're actually stored as a typical file format, and they typically utilize clusters to store that data. And clusters, of course, are made of one or more sectors. So the images are stored in sectors, clusters, and within the file system. When you have all of the information in your file system to recover a file that's been deleted, that's called an active recovery. The photo isn't deleted, but it sees the file system, and the information that points to that photo cluster is present, and so all that's left then is to actually do the work of putting it back together again. And here you see an example of how the three clusters for the hello.jpg are all contiguous, and so it's really easy to put that back together again. But the hk.jpg is much more problematic because it has the first section, then it has a middle section that is the da.bmp, which is just kind of plunked into the middle of this file storage, and so you have your typical fragmented file system. And if you delete some of them, it will be very difficult to be able to recover these by just looking at them. So one way to do that is carving. File carving is where we're going to extract and recover files based upon their structure, not on the information provided to us by the file system. Many file formats have some code at the beginning and the end of their files called headers and footers. And if we can search for these headers and footers, then we can recover the beginning and the end of those files. But it's not enough to do that very often. Sometimes we can go carve just the right amount of space, and we'll be lucky and actually get a file. Sometimes we won't. But we have some other methods, smart carving and guided carving, that will help us overcome some of these limitations. File systems don't actually wipe data, so the data is usually there. The file tables may be corrupted or missing, but typically they themselves are still around and available. The device itself, worst comes to worst, it's formatted, in which case you may not be able to recover the data. But generally, if you know there is data there, you can find a way to parse that storage device and to carve out that data. Header and footer carving is, of course, the most down-to-earth version of this. And we typically will try to identify a cluster with a header, the starting signature of that file format, and then try to find its footer, and then merge all the clusters between the header and the footer, and present it to the user and say, is this in fact a valid JPEG? And sometimes they'll say yes, or sometimes they'll say no. As you can see here, we have an example of looking for headers and footers. We can find the header with the FFD8, and then it knows that there isn't a header or footer in the next one, or it knows that it's there but it's not the right one, and then it goes to the next one and finds the footer, and then it puts the two of them back together again. Fragmented recovery becomes a little bit more difficult, but you can still do some, but very often it results in an incorrect recovery. And so you end up with something that looks like either of these two pictures. You can see the incomplete photograph there. Similarly, the photograph that you see here. It really could be important to get all of the photo in there, and so we need to find a way to do that. And Digital Assembly has spent a lot of time and money to figure out how to do that. They say that for starters that about 6% of the files on a disk are fragmented, but an even larger proportion of JPEGs are fragmented. And the more the disk is used, the greater the rate of fragmentation. So we need to find a little bit better way of doing it. One way of doing it is to just, guess. Basically find headers and footers and put them together. And sometimes we're right and sometimes we're wrong. On the other hand, NTFS can help us because it can provide us with logs of the cluster information on deleted information. And so we can very often recover a fragmented file by looking at the NTFS logs. But we typically need even more data to validate what we're doing. And one of the ways we can do that is by looking at the characteristics of the data itself. What are the color mapping and the color tones, and how do the edges match up to other edges on a cluster by cluster basis. Smart carving is Digital Assembly's proprietary technology for recovering it, and the analogy that they like to use is it's not just a matter of trying to put one jigsaw puzzle together. It's imagine that you actually put several different jigsaw puzzles together on a table and trying to figure out which ones belonged to which jigsaw puzzles, and to solve all three of the jigsaw puzzles at the same time. And it uses validated carving and actual photo content to identify where the image may be fragmented, and it looks around for the next fragment, and it does this to a lot of different images, a lot of different sectors all at the same time, and that's kind of the magic behind smart carving. And you can see kind of notionally how we look around and find these different bits and pieces, and we progressively are able to put them in piles together, and then we're able to rearrange those pieces until they create an actual image or the correct image in each case. Cluster size is important because carving typically is done on a cluster boundary. The problem with that is that if you change the cluster size, then it's going to change where that boundary is. And so if you have a card that was formatted at 2K and then you put it on 4K, it's going to be very hard to find the footer information because it's going to be in the middle of a cluster, a larger cluster. If we only carve by cluster, we're going to get some that we're just not going to be able to recover. Whereas the solution for that is to do sector and byte level carving, and it will look at all the clusters not allocated to a file and determine if it ought to be part of some file out there. Does it fit into some other file out there? In some cases it will look at the header signatures, but it'll also look at sector boundaries, and it looks at it intelligently. Embedded carving is where you're trying to get images out of container documents, such as the XML versions of Word documents, zip files, PDFs, etc. And the goal there is to get the photos without having to look at the rest of the document. And extracting photos from a compressed file like a zip file requires that it be decompressed first. Most forensic carvers don't have decompressors, so they very often will miss these images. Adobe Forensic Photo does. And content analysis is, what's it about? Does it have anything of interest to us forensically? And how do we know what's interesting and what's not? And that really is one of the hardest parts of it. The good news is that we have some tools now that we can arrange photographs by the date taken and some of the metadata and some of the color schemes and that sort of thing, which may help us to organize it. We can look for photos that contain pornography, or photos that have faces, or any image that's been manipulated, hidden photos, and that sort of thing. So we're developing more and more tools to be able to do this, but it still is by far a far more manual process than we would like it to be. The problem too is that typically, in order to look at a large number of these files, the examiner is going to use thumbnails which don't have very great resolution, and it's pretty hard to look at all of the images even when you're only looking at thumbnails. Well, that's it till next time. Have a good day.